Okay, so good afternoon for those who have already joined the call. I'm sure some more people will be joining, but we'll get started. So thanks for coming to this webinar, Real World Data in Medical Research, Harnessing Their Potential and Addressing Challenges. My name is Oliver Blake, and I'll be acting as the moderator today. I work for LIBA Europe, Europe's Association of Research Libraries, and we participate in the MES-CoBraD consortium, one of the projects we'll be presenting today. The event that we've put together for you is a collaboration between 3 European projects funded by Horizon Europe. That's Resample, Retention, and MES-CoBraD. Resample works to transform the healthcare journey of patients with chronic obstructive pulmonary disease. Resample uses real-world data to monitor symptoms beyond scheduled medical checkups. Such information will give doctors, caregivers, and patients a unique insight into common day-to-day triggers that can lead to health complications. The data and analyses will feed into the development of personalized treatment and a virtual companionship program. The second project that we have is Retention. This is a project to support clinical decision-making with data-driven interventions for heart failure patients and patients who received a heart transplant. By utilizing real-world data, the project will develop state-of-the-art technical solutions to provide personalized interventions for patients. The resulting platform has the potential to improve hospitalization rates, quality of life, safety, and well-being. And last but not least, we have the MES-CoBraD project, the third of the 3 projects today. And MES-CoBraD aims to improve the diagnostic accuracy and therapeutic outcomes in people with complex brain disorders. The project uses data from multiple clinical sources in effort to create comprehensive, cost-effective, and fast protocols. The consortium consists of experts from medicine, engineering, computer science, as all the projects do today. And MES-CoBraD is trying to improve the quality of life for patients, caregivers, and society at large. Across the next 90 minutes, you'll hear a lot more about each of these projects, and you'll get an in-depth look at how they use real-world data to tackle complex medical challenges. Across the 3 presentations today, our panel of experts will delve into how their data was acquired, harmonized, stored, utilized, touching on the challenges and processes involved throughout their projects. We hope that this webinar begins to demonstrate how the work of these projects aims to transform the delivery of healthcare, improving patient outcomes, and creating more accurate and efficient medical decisions. So to give you an overview of how things will run today. So shortly after I stop speaking, and you'll hear from each of the 3 projects with a 15-minute presentation. And this should leave around 30 minutes for a discussion amongst the panel of experts. This discussion will be an opportunity for our speakers to share knowledge and experiences with each other. Actualizing the potential of real-world data is a common theme in each project, and I will ask the speakers to engage with each other and share common challenges which they have faced and reflect on the different approaches they've used. Ideally, this should be an opportunity for the projects to learn from one another, as well as you, the audience. But we do also want to hear from you. If you have questions for our speakers, please write them in the chat function. And if it's for a specific speaker or a specific presentation, please make it clear who you would like this question to be addressed to. But before we kick off, I have a few notes of housekeeping just to make sure our event goes smoothly. So first, I would ask the guests to keep their cameras off and the microphones muted to avoid any interruptions during presentations. When you signed up, you were informed that this would be a recorded event for future dissemination. This is also why we ask you to keep your cameras off. And finally, as I just explained, we do want to give you the opportunity to engage with our speakers, but put the questions in the chat, and then I will put these to the speakers on your behalf. So without further ado, I would like to welcome the first project of the day, which is Resample. I will invite Anka and her team to have the floor, and you can introduce yourselves. And you have 15 minutes for the presentations. Thank you.
Yes, thank you. Hopefully you can see my screen. Yes, okay. Thank you for the introduction. My name is Anke Lemfrink, and I'm working as an assistant professor at the University of Twente in Enschede, the Netherlands, at the section of Health Technology and Services Research. And I'm acting as a clinical coordinator of the European Resample project. And today I shortly discuss an iterative process of real data collection that we do in Resample. And afterwards, Christos Kaloniatis will talk about the privacy issues and privacy challenges that we face in Resample. So Resample is real-time data monitoring for shared, adaptive, multi-domain and personalized prediction and decision-making for long-term pulmonary care ecosystems. Our project is now running for about 2.5 years, and our consortium consists of 10 partners in Europe, and we are specialized in respiratory medicine, in real data, artificial intelligence, privacy, ethics, data protection, and also health policy. So as you might know, there are more and more people living with chronic diseases, and also because of an aging population. And COPD, chronic obstructive pulmonary disease, is one of them. It's a really high impact disease. It's the third most leading cause of death globally. And also it results in many exacerbations, which are flare-ups of respiratory symptoms like shortness of breath, sputum production, etc. And that causes many hospitalizations. So as it is a progressive disease, we really need adaptive, predictive, personalized self-care and a focus on prevention and lifestyle. So our Resample project objective is to identify exacerbations and flare-ups of not only COPD, but also of the comorbidities, so that we can develop tailored referral to a multidisciplinary adaptive virtual companionship program. And that we do by identifying a monitoring profile to make risk predictions on, so that we can make shared decision making with tailored interventions. So what we expect that this will lead to is less scattered care, less hospital-based visits, and more towards proactive disease management. So the patient needs to be in lead, and by having a risk profile of these patients, we hope that we can step up the care if necessary and also adapt the care plan towards the needs of the patient. So what do? We created a real data lake. So we do all kind of measurements in daily life at care centers, but also at shared care facilities, in order to identify patterns of symptoms, but also to look for predictors of disease progression. And by scientific evidence and medical guidelines, we try to come up with a risk profile of patients to open discussion during the decision making, not only with the patient, between the patient and the healthcare professional, but also by use of the technology, so that we can offer patients appropriate treatment. And we are currently developing an adaptive virtual companionship program, including coaching elements and personalized action plans to help patients to treat their symptoms. So how did we come up with the predictors that we use for exacerbations in our Resample project? First of all, we tried to make that knowledge base. So we conducted 3 systematic reviews. They are all written down here. And we used clinical guidance, but also retrospective data of clinical studies that we have done previously in the hospitals. And we ask our users, so patients, but also healthcare professionals, to come up with their preferences, their requirements, and their needs, so that we could try to align the predictors and the parameters with the evidence that we know. So in the beginning of 2022, we did set up a cohort. So this is a multi-center observational monitoring cohort that we are running in Tartu University Hospital in Estonia, in Medisch Spectrum Twente, Enschede in the Netherlands, and also in Gemelli Hospital in Italy. And all patients are using an Healthentia application and a cloud. And we have there multiple sources of data available that we collect during baseline, daily, and during deterioration. So we have questionnaires, we have data from electronic health records, we have biomarker data, we have activity data, and environmental data. And we provide AI service for all patients and use a privacy by design approach for this. Here you can see an example of a daily symptom diary, which we made digitally available so that we can measure each day the symptoms and the increase in symptoms of every patient, not only for COPD, but also for heart failure, for anxiety, depression, diabetes, and ischemic heart disease. Our cohort and the parameters that we collect is continuously evolving. So we took an iterative approach with focus groups, including healthcare professionals and also patients, to come up with data that we really would like to measure and to collect. So to optimize the data collection of predictors of exacerbations. There were some additional parameters proposed by the clinicians and by the patients, like fatigue and body temperature, but there were also some reductions of the number and frequency of questionnaires and parameters that we measured. So in the end, we have 6 themes of real-world data of predictors that we measure. These are patient characteristics, comorbidities, biomarkers, lung function parameters, symptoms, and composite parameters. In a resample, as you heard, we have many data that we collect. So we have basically 2 data sets that we are working with. One is the retrospective data set, in which we use the data that we previously collected during clinical research and also during usual care at the 3 pilot sites. And we try to align all the variables in from different formats into one format. And also we have the prospective data sets in which we collect all the variables that we collect during the cohort studies at the different pilot sites. So from the hospital information system, from Healthentia, from the air quality databases, and we aggregate those in so-called edge nodes that we created at the 3 hospital sites. And we used uniform HL7 FHIR compliant data formats for that, to do that. And now I will give the floor to Christos, who can tell you more about the privacy challenges in our project.
Thank you very much, Anke. Hello all, my name is Christos Kaloniatis. I am a professor on privacy requirements engineering topic, representing University of Piraeus, one of the partners of the Resample project. I'm also serving as a Resample data protection officer of this project. So our main role here is to try, it's twofold actually. First of all is to try to enhance privacy in all this, in this complex but very interesting system. And in parallel try to preserve all the GDPR related concepts that we have to follow as a consortium during the development of this system. That's why I would like on the second part of this presentation to share with you our the efforts that we did in both cases, the lessons learned so far. The project is still running, so I'm glad to discuss any ideas that we may have on the things that we are dealing with. So as you can see here, it's the high-level architecture of our system. As you can see, the reason that I'm putting this slide is because I want you to see a little bit the complexity of the system that we're dealing with. So we have this. We have the edge nodes, as Anke said before, installed in every hospital. We have an orchestrator, which is an external module, try to orchestrate the knowledge that we get from the models and the trainings in order to pass in a safe way in all 3 pilots in the hospitals. Privacy by design plays a key role, not only in the development, but also as a mentality of the principles that we have to follow in order to keep the data private, but also, of course, make a trustworthy system. Which are the challenges here? We're dealing with a secure multi-party computation among the 3 hospitals. We're dealing with federated learning, things that have a strong AI character, which increases the challenges that we have to deal with regarding privacy. So next slide, please, Anke. Here you can see the diagram of, if you can, yes. Here you see an abstract diagram of the resample assets. So as you can see, there are 2 main blocks. The one block is the edge node, which is the main component installed in every hospital. And there all the data handling occurs, all the processing from the data of the patient's data from every hospital occur. This module communicates with the orchestrator, which is outside the hospital. So which data should pass along the orchestrator in order to be trained, which data the orchestrator feeds to the edge node is still a challenge. And of course, we have on the left side of the slide, you see Helvencia. Helvencia is the tool that we use to feed and provide all this coaching to the patients. Again, this was also a challenge because we want this to be protected. The data should not leave the edge node, but in parallel, the knowledge that Helvencia needs in order to provide the coaching to the patients is we should still keep that accurate and with a high level of integrity, but also secure. So as you can see in this high-level diagram, the challenges that we deal are in 3 levels: in the orchestrator, in the edge node, and in the part that communicate with the edge node. So the next slide, please. So here is another diagram where you can see actually the security domain. So I'm putting this slide just to tell you that it was a huge discussion on where the boundaries of the security is among the resample assets. So we try to understand, to map all this complex system and where the security actually needs to take place, where core resample assets needs to be protected. And we deal with this huge risk analysis process for being able to safeguard the data inside the dotted areas that you can see here. For example, the red one, which is the edge security domain, as you can see, how we're going to protect these assets against potential threats and attacks, but also keeping it safe for the rest of the parts of the resample architecture as well. So if we move on forward, as you can see, the security model of resample actually had the issue of authentication and authorization. The issue of authentication and authorization is because we have a lot of assets that need to be authenticated before they communicate, before they contact each other. We have 2 types of authentication, machine to machine and user to machine. We followed the OAuth to an OpenID Connect protocols for authentication and authorization. And of course, we needed and we developed a dedicated resample role-based access control policy for handling the situation. Also, we had objectives regarding the identification of patients, which is very, very important. So we use patient pseudonyms, visible at the interface of the edge node, but never stored in the edge node. And the patient pseudonyms and location-related information never took part on the training datasets that we used. Also, there was a discussion about the security perimeter, as I told you before. So the decisions were that no incoming connection requests should come to the hospitals. Only outgoing connection requests come from the edge nodes to the other 2 nodes that I showed you before, the group of assets, actually, the orchestrator and the Helvencia. So moving things forward, there are some facts that we considered before dealing with the privacy-related issues and challenges. First of all, we had multiple partners contributing and collecting also different data types, different types of data. That was one challenge. And also we had data collected from various sources. And also we had the partners, the more technical partners that were not involved directly in the data collection, but were mandatory to get the data in order to train the machine learning models. So the data, all this data collection should follow specific principles. So the first principle was that the intended resample, we need to safeguard the intended resample functionality, the user requirements that we had, and the functional requirements of resample, to follow the resample architecture and respect the resample architecture. Of course, the requirements that we already have promised that we should fulfill when we were drafting the proposal. which are also the minimum goals that the resample architecture, the resample solution should satisfy. And of course, what hospital actually can offer in order to satisfy our specific requirements. So these were the facts. And as I told you before, Anke, we can move on to the next slide, please. As we said before, the challenges were twofold. The first challenge was to make this to design an architecture and create a resample platform that is follows the GDPR compliance and the privacy protection of users, but also try to keep the processes inside the consortium following the GDPR regulation and the basic principles. So, how we overcome the issue that we had hospitals and technical partners needed to gather data and train the models? We followed the internal agreements process. So actually we had we specified in detail the purposes of processing for every activity. And I want to mention that in more detail, not only the purpose of processing that the resample will serve at the end of the project, but the purposes that we need internally in order to satisfy GDPR by disseminating data among the partners. This was achieved by drafting specific agreements. We had a joint controllership agreement among the 3 hospitals. We had a data processing agreement between the clinical partners and the technical partners. And again, we had a data processing agreement between the clinical partners and Healthensia, which I told you, Healthensia is was the part of the left, is the partner that deals with the companionship program and the coaching of patients. So this was a lot of work, but it made all explicitly clear to all partners what they contribute. They binded that with specific agreements. So now we are free to proceed. And we did that already in the implementation stage, where all the data are legally distributed inside the consortium partners. The second challenge, Anke, we may proceed. The second challenge was to create a framework where we try to combine all these legal and organizational aspects of GDPR along with the technical aspects of dealing with reasoning with security and privacy in order to satisfy, first of all, to identify and then satisfy the technical security and privacy requirements. For that, we have developed a specific framework of these 11 steps, as you can see here, that we combine actually following a specific risk analysis process. We combine, we identify all the threats and potential vulnerabilities based on the resample assets, and of course the specific requirements that we have to fulfill, in order to end up proposing specific security and privacy measures with a specific impact calculation on every decision, in order to end up with a list of specific security and privacy technical requirements that, along with the organizational and legal requirements, form the set of requirements that aim to protect patients' privacy. And of course, fulfill also all the other requirements that the legislation enforces us to do so. As you can see here, it was actually a demanding task because there was a lot of knowledge, a lot of potential threats and attacks that we found in the literature that we followed and we mapped and we deal with in order to end up with this specific list, which led us also to the proposal of the specific countermeasures that the resample technical partners and developers should follow. So all this process actually took us about a year to enforce, to implement, to deal with, and a lot of discussions with our technical and clinical partners to manage to apply this framework. And now we are happy to say that we are in the phase where we are trying to adopt the security and privacy technical controls and countermeasures based on this analysis. Next slide, please. A couple of slides before we finish, I would like to raise also a very important aspect that we deal with since we had the real-world data and patients' data, was about open data. So we had a huge discussion how we offer open data to public, how we endorse patient pseudo-anonymized data, or if we should, and which data we should have open to the public. So based on this DPR, things are a little bit contradicting. First of all, when we're talking about research, things are more easily. For research purposes, we have this ability to open data to the public community. That's good. But in order to provide anonymized data, and this is something that we find it in many cases that many partners are trying to understand, and I think that in an example we moved this one step forward, is that the anonymization of data is still a processing on personal data. And what we should not forget is that any type of processing on personal data at least needs patient's consent, needs user's consent. So it was explicitly clarified that we need to have the consent of the patients for anonymizing their own data if they agree that this data could, in an anonymized form, can be open to public, or we can offer them to the research community. The two paths that we offered to the consortium was, first of all, we can anonymize data based on specific requests, and we examine this request. If we agree on the request, we anonymize the data for serving the specific request, and we provide it. And the other part is we anonymize the data for a specific generic purpose related to research that we can offer it to the research community. And our decision was to follow the second, thank you, Anke, yes, the second path. And what we said to the clinical partners is that this is not mandatory to be done horizontally, meaning that every clinical partner can decide the purpose on which they can anonymize the data and offer them to the research community. So every clinical partner has to define the purpose of processing, inform the data subject, the patients, and then conduct the anonymization. They will be responsible for conducting the anonymization. Since then the data are anonymized, then, and if we have an informed consent from the patients, then of course we can offer the data publicly available. Of course, the technical partners, the partners that don't own the data, can neither provide by themselves open data to the research community or involved in the anonymization. This is clear that the anonymization should be conducted by the owners of the data, and the owners of the data in these cases are the hospitals and the hospitals only. I think that all these findings are, I would like to say that, are the result of a lot of discussions, and I'm very happy that we had a consortium where the clinical partners and the technical partners, and we had a common understanding of the privacy issues and the GDPR compliance issues, and we all together find these approaches as valid in order to accomplish our goals, and in parallel create a trustworthy and privacy-aware platform for our patients. Thank you very much for your attention.
Great. A big thanks to both Anke and Christos for sharing some of their insights from the project so far and how they've managed to balance these competing demands with the technical requirements, the clinical partners, etc. I'm sure that will be a theme throughout the rest of the presentations. If you do have questions, we'll have time to ask them at the end during the discussion, so I'll put them in the chat. And I would like to move on to the next project that we have today, the retention project. We have Nicholas and Mary from that project. I will leave the introductions up to you two, but yeah, the floor is yours for the next 15 minutes.
Good afternoon from me. I hope to see my presentation. So my name is Mary Rumbi. I'm a researcher from Foundation of Research and Technology in Greece, FORTH. FORTH is a consortium member of the Intention European funded project. So today I will share my presentation. The presentation will be shared between me and my colleague Nikos Vasiliou, a PhD researcher from ICCS in Greece. I will start the presentation presenting you how we explored the real-world data derived from continuous monitoring of patients that suffer from heart failure, and then Nikos will continue giving you more details about FHIR resources and how we can manage the healthcare data exchange. So, okay. I will start with a brief description of the heart failure disease. So heart failure is a chronic disease with several comorbidities. that has become the main cause of premature death in the world. So the prevalence of heart failure in Europe is 1 to 2% of adults, and it increases with age from around 1% for those aged with less than 55 years of life to more than 10% in those aged 70 years or over. So heart failure is considered as a heavy burden on health systems due to the multiple and also very prolonged hospitalizations of patients and the high patient management costs. So recently, the heart failure guidelines from the European Society of Cardiology have stated that the non-invasive telemonitoring may be useful for the heart failure patients, but we need more evidence about this. So the current clinical practice mainly focus on the early visit of patients admitted for acute heart failure in order to prevent readmissions. However, no other recommendations are made, and the follow-up of patients is strongly dependent on the country and the specific country and the specific clinical center. So according to the literature, there are numerous studies that indicate some parameters with strong evidence for remote monitoring. So as you can see from the table below, we have different type of variables that are associated with the specific type of patients that we handle in retention: heart failure patients, heart transplanted patients, and left ventricular assist device patients. So, for example, the vital signs variables are considered as high priority variables, and this means that comes mostly from the clinical practice, according to the literature. But also we have some other type of variables like activity tracking, like sleeping or environmental variables that are considered as intermediate priority variables. This means that there's some significant evidence that can be associated with the patient status, and in this sense, we are expected to enhance the analysis of the patient status. So based on that, and in order to exploit the power of real-world data, a more in-depth observation of the variables is needed in order to achieve a better patient management, including real-time monitoring and also feedback from real-world data. And here it comes the retention concept. So the main aim of retention is to develop an innovative platform that supports personalized interventions of patients that suffer from chronic heart failure diseases and reduce cardiovascular mortality and hospitalization rates. So this will be achieved through the collection and exploitation of real-world data coming from the continuous monitoring, and along with the integration with other diverse data sources to extract the relevant information about the patient's health status. So for the data collection and also the patient monitoring, each of the patients is provided with devices such as a smartphone, wide scale, smartwatch, blood pressure monitor, oximeter, home temperature and humidity sensor, and a home local gateway. So these patients are participating in a randomized clinical trial that is that will take place in the framework of retention project, and are recruited across 6 hospitals in 4 different European countries. So the integration of the heterogeneous data that we have in retention, and I mean demographics data, baseline, follow-up, medications, questionnaires, and also included the real-world data. This is considered the main challenge and the main asset of retention because it allows the extraction of useful information which is hidden in data collected from patients' daily life. So what we need here is to follow a specific pipeline in order to harmonize the different types of data. So first of all, we have to, and we already did that, is to design the retention reference model. So reference model means we have a set of variables that are chosen by the clinical experts regarding the 3 different types of patients, and is in line with the retention clinical protocol. So according to the reference model, as you can see on the figure, each patient is linked with different types of data. Each of one has 1 or more parameters. So each variable in the reference model has its own type and its own parent class. For example, we have the variable, have the class demographics, and so we have the variable gender. The variable gender belongs to the class demographics. So after completing the design of the retention reference model in collaboration with our clinical partners, then we have to define the data model. So as the data model is defined as an abstract model that organizes the data description, the data semantics, and also consistency constraints of data. So the definition of the data model is driven by the analysis of international standards and is compliant with 5 specifications that adopt terminology systems such as LOMIT-CT, LOINC, ICD-10, or APC in order to facilitate the interoperability of the system. So as you can see here in the 2 tables, we have 2 different classes, cardiopulmonary exercise test and VAD measurements, and each of the all the variables for each of the class are coded with the specific terminology systems. Also in the second table, you can see that there are some variables that are not mapped with any terminology system, and we code it as other. But in retention, we consider them as very important variables for the clinical protocol. So we included in the data model. So the retention semantic data model was designed and developed under WebProtege. WebProtege is an open source ontology editor and framework which transforms the reference model into an ontology, a semantic data model, and support different file formats like XML. So the main scope of the data model is to enable the storage and also the processing of the heterogeneous data during the platform operation. And here in this figure, you can see a visual representation of the hierarchical relations, yes, among the classes and the subclass of the ontology. So we have 2 object properties were defined in order to link the classes with their corresponding subclasses. We have the object property has and the object property include. So for example, the class patient has demographics, baseline history, medication, clinical data, etc. And another example, the patient, the class patient has questionnaires which include the custom questionnaire, the mock questionnaire, etc. So the ontology represents the data in the form of entities, meaning classes and also object properties. The nodes, as you can see here, correspond to classes and subclasses. So this is a view of the real-world data sensor class with its corresponding data properties and also data types like float, integer, etc. I can show you another example about the data model. For example, a detailed view of the echocardiography class with the corresponding data classes and also data types. Echocardiography class includes 40 terminologies with mixed data types. So now my colleague Nikos is going to present you more details about the FHIR resources and how we map the data model to FHIR resources.
Thank you, Mary. Okay, we'll start with the definition of FHIR. FHIR stands for Fast Healthcare Interoperability Resources. It is a standardized data exchange protocol developed by Health Level 7. And it is designed to facilitate the exchange and management of healthcare information among different healthcare systems, such as electronic health records, mobile apps, wearable devices, and other health-related technologies. FHIR utilizes modern web standards like HTTP, RESTful API principles, and JSON or XML formats. FHIR resources are the fundamental building blocks of the FHIR standard. The most important FHIR resources used for the retention project are the patient, which represents information about an individual receiving healthcare services, observation, which records observations made about the patient's health status, such as vital signs, lab results, etc. Medication, which describes medication and substances prescribed to a patient. Encounters which describe every aspect of of an encounter between an individual providing healthcare services and an individual receiving. Conditions which represent a patient's health condition or diagnosis, and various questionnaires. Next slide, please, Mary. Okay, the main advantages of FHIR is interoperability. FHIR promotes interoperability by providing a standardized way to exchange healthcare information among different systems. Modularity and extensibility. FHIR resources are modular, allowing for easy customization and extension to accommodate specific needs or additional data elements without disrupting the existing structures. As mentioned before, the modern technology standards like RESTful APIs, JSON and XML formats used. The scalability, FHIR's design supports scalability, allowing healthcare systems to efficiently manage large volumes of data and accommodate increasing demands for healthcare information exchange. And the patient-centric approach, which FHIR emphasizes a patient-centered approach by providing APIs that enable patients to access and control their own health data, fostering patient engagement and empowerment. The main disadvantages of FHIR, the main is the implementation complexity. While FHIR standards aim for simplicity and ease of use, the actual implementation can still be a little bit complex. Data quality and consistency. Sorry, I've got a cold recently, so you'll have to excuse me. Maintaining data quality and ensuring consistent data representation across different systems can be a challenge. Standardization and adaptation. Despite being a widely accepted standard, achieving universal adaptation and standardization across all healthcare systems and organizations globally remains a challenge. And one huge aspect is the integration costs and time. Integrating FHIR into existing healthcare systems might involve significant costs, time, and resources, particularly for organizations with complex legacy systems. Next slide, please, Mary. Another important aspect already mentioned from Mary is the mapping of the variables to international terminology and coding systems like SNOMED-CT, LOINC, ICD-10, and ACT. Next slide. Okay, now we will move to the most technical aspects regarding the retention project. For the needs of retention project, the FHIR server was set up. It was based on the Happy FHIR Starter project version 6.0.1. And regarding the FHIR version, R4 was used, which was the latest version at the time of development. Now I think we have moved to R5 FHIR version. Happy FHIR Starter project provides a web interface, which you can see in the picture. We can customize the interface, adding the project logos or various links to the project's websites, etc. And this was deployed as a Docker container. Although the web interface will not be used during the clinical study, no one will have the ability to access it. It provides a useful playground to get developers familiar with FHIR, the resource schemas, the RESTful APIs, search queries, and things like that at the early stages of the project. Next slide, please, Mary. So the next step after setting up a FHIR server is to provide an implementation guide. This acts as a contract between the developers and the FHIR server. And it includes 3 steps. The first step and the most challenging one is the creation of resources. This was implemented via the FHIR Forge. And it includes the creation of custom profiles and extensions. For example, for the needs of the retention project, we needed to extend the basic FHIR patient profile in order to include parameters such as the patient's educational status, the patient's employment status, living conditions, etc. Code systems which aim to fill the coding gap where the international coding systems such as SNOMED and LOINC cannot describe a variable, like the VAD measurements mentioned by Mary before. And the most important are the examples, which was very challenging. Retention contains, I think, about 450 variables stored in FHIR. So for each one of them, we had to provide an example for developers to follow. The second step includes the conversion of the generated resources to the FSH format. FSH stands for FHIR shorthand. This was accomplished via an online tool that converts JSON objects or XML objects to FSH. And the last step is the implementation guide generation, which takes all the FSH resources as input and provides a web interface including all those resources. We could have a short demonstration in the next slides, please, Mary. This is the homepage of the implementation guide. Again, we can customize adding logos, useful links, etc. Next slide. Here is the table of contents, including every variable, as well as custom profiles, definition of questionnaires implemented for the project. And final slide. And here we can see an example of a variable of the retention project, which is distance. On the left side, we can see a general description of how the variable is coded in FHIR. We can see the code, which is SNOMED city code, value accompanied by its unit, while on the right side, we can see the JSON representation of distance. That's it for me. Thanks for your attention. The mic is back to Mary.
Yes, we are a bit out of time, but I would kindly ask Oliver to give me 1 more minute to finish with 2 more slides. Considering the retention data model and also the implementation guide and the FHIR sources that Nikos presented, I think it's very important to provide to the users an open data setting specification that will form the basis for the clinical and also real-world data setting from retention platform and also to retention platform. So the main goal of data setting to retention platform is to enable third-party users to leverage retention, bring their data to the platform, and join the retention initiative. So the advantages are great since the external data can increase additional data point in retention used for model training and increase the model accuracy. So the user here, by clicking you can see here two mockups. This task is under implementation and under development in retention. So what we are going to do is to develop an application of a simple graphical user interface that will let a third party to import the data according to the retention data model in a specific format, a specific structure. So what the user has to do is by clicking the input data option to import new data to the platform that will be corresponding to new patients. So the user should prepare a CSV file, as you see on the right figure, and import the CSV file that contain all the information. And so after uploading the CSV file, the next option is the post data option. So having already imported the CSV file, the user is ready to send the data to the cloud. So here we have we use 2 main endpoints for posting the data. One we have for FHIR data and the other one for non-FHIR data. So moving forward to the data setting from retention platform, and it's very important to say that this task enables external users to receive the project's data and also use them for their own research needs. The challenge here is to implement the process of enabling third-party users to easily download all the data to their local machine, all the anonymous data, let's say, to their local machines. So what we are going to do here is also to develop a simple GUI tool in order to facilitate the whole process of downloading the data to the database and also provide the implementation guidelines. So when the user clicks on the Get Fire Data option, a background process is initialized that implements multiple GET requests in the database for the Fire endpoint. And the same process is followed for the non-Fire also endpoints. So when the process is finished, the software creates a local folder which is called the retention data, as you see on the right figure, that contain all the exported JSON files for each patient. We have all the anonymous data for each patient here. We have for each patient, we have one JSON file for file data and one for non-file data. So finally, then the user can use the implementation guidelines option in order to redirect it to the implementation guide link and also see information about the data structure. So this task makes, let's say, the open source distribution of the data possible, and several key outcomes also can be achieved from this, such as the exploitation of the data for training the models of the external users. And this is all from us. So I would like to thank you for your attention.
Okay, thanks to Mary and Nicholas for the presentation. We're running slightly over time, so I'll quickly hand over to LCS from MES-CoBraD. Keep the questions coming into the chat for the discussion, and all the presentations will be shared after the event as long as the video. But now the floor is yours, LCS.
Hi, everybody. I'm Alexis Georgia. I want to share the screen. That should work. I'm a behavioral neurologist and a sleep physician at the Neurological Institute of Athens in Greece, and the scientific director of the MES-CoBraD project. So, as an overview, the multidisciplinary expert system for the assessment and management of complex brain disorders, so MES-CoBraD, as it's self-explanatory, is a partnership between 14 organizations across Europe and Israel. And it aims to tackle three main categories of challenges. Clinical challenges, so in general, how do we improve diagnosis, either timely diagnosis or accurate diagnosis? How do we improve treatment efficacy or identifying treatment side effects that we may not be aware of? Then research challenges, how do we fill the gap on the pathophysiology that exists, or how do we pursue clinical trials with medications that eventually may be effective? We've had a lot of trials in brain disorders, especially in degenerative diseases, where there was a failure after failure after failure until some medications seem to be effective. And then a lot of technological challenges. How do we integrate data, especially if we're talking about real-world data, in ways that are usable, efficient? How do we also not just integrate and represent data, but also how do we analyze them in optimal ways, so using machine learning, artificial intelligence, and aiming that, putting all these challenges together, helped us identify ourselves as a project. That means being a project where we tackle brain disorders to improve people's quality of life, but also improve healthcare systems, and for improving diagnosis and treatment. And we focused on three main categories, three main diagnostic categories that of brain disorders: epilepsy, dementia, cognitive disorders, and sleep disorders. And the reason is that they have individually high morbidity and mortality, but also they are highly comorbid. So if you have one, it's much more likely to have the other, with much worse outcomes. And in this setting, how do we combine elements of real-world data in cost-efficient, fast protocols, leveraging technology, not just as a data repository platform, if you want, but also a place where scientists can do analysis, so develop new knowledge, but also clinicians can use the MES-CoBraD platform as a decision support tool in real-world settings. Can I become more of an expert, even not an expert, if I'm in a rural island in Greece, for example? And that's where you have people from all the different disciplines, from medicine, engineering, computer science, amongst others. And this solution cannot be static. It has to be dynamic. We have evolving ecosystems all around us. There's a big breakthrough in artificial intelligence over the past year or so. We have new technologies coming that are task-specific. So you cannot just say that whatever I produce is a static solution. So whatever you produce has to be a modular solution, where components of it can be updated or replaced with new ones. But the philosophy in the end, when you think of it on a very high level, is a framework where you work on. And that's where we have this dynamic modular solution, where you have patient participation with enriching data every moment with even new, potentially, types of real-world data that inform our research. So you have evidence-based, data-driven results. And these, in turn, can apply into clinical practice, where you get clinical application for decision support. So this is an infographic we prepared a couple of months back. We have we have more than 610 participants in our project. About 80 of them come from retrospective data, with more than 5,000 or 6,000 now samples. And then we have different types of or categories of samples processed. We have analytics functions for doing data analysis, and also visualization tools. So some key components of the MES-CoBraD solution. First of all, there are simple things that are already implemented, comparatively, where a patient and their caregiver can provide information from home. If you think of a patient with dementia, the information cannot just come from the patient. You need a caregiver, and that association is relevant as we acquire data. It also allows us to see how does a patient's condition affect a caregiver. It's important to think of the system you are treating, not just an individual patient. Then we have edge tools. So within an institution, edge module tools where the data are combined, analyzed, pre-processed. And then on the cloud level, AI, advanced analytic tools, and expert system tools that can work as clinical and also research decision support tools. Within the framework of open science, this data can be anonymized and depersonalized, and we'll come to that, within the MES-CoBraD platform for other researchers as well. And in this way, having a multidisciplinary environment across disciplines. So we implemented the protocol, prospective protocol. It is based on a simpler protocol we had been pursuing at the Neurological Institute in Athens previously, but we expanded on it. And it captures the multidimensional elements of our real-world data, from clinical symptoms, physiology, cognition, biosamples, imaging, and so forth. But not just as individual observation, but also their dynamic temporal relationship. So as you will see, a person comes in through our protocol, they answer questionnaires, they have a structured examination, so the clinician also answers questionnaires. They have a traditional cognitive test, and then they take an actigraph that measures their activity and indirectly their sleep over a week. And at the end of that week, they have a sleep study with a full EEG. So we capture at the same time sleep and epileptic components. Before and after sleep, we have what is called sleep-mediated cognitive testing. And the reason is that it captures better, or in some elements, it allows more sensitive early detection of cognitive changes, how you did the previous night compared to the next morning, maybe more sensitive than certain absolute levels. So That's one component, but also the same thing applies for biosamples. Your proteins have fluctuations throughout the daytime. So this delta before and after sleep, different times of the day, are important. And these are things we want to capture within our real-world data. And then other components as imaging or medical device data or app devices for sleep apnea and so on. So that's an abstract system architecture to our solution. So we have a cloud service outside the institution, but also edge module services that connect or are able to connect to electronic health records or portals to patients. So on a cloud level, you have a metadata manager where the semantic ontology of the variables that you have linked to questions, also in questionnaires, resides. The data analytic tools, a central data lake with every post-anonymization, of course, and a workflow manager. The workflow manager is a component that represents two things. It represents processes that have to do with analyzing data. So if you take the datum, you pre-process it, let's say you pre-whiten a time series, and you take, I don't know, you filter based on sex or something, and then you decide to do a simple t-test. So that would be a linear flow. But then if you're a clinician, you want to get the first piece of information in, you process it, then you fit it into the rest of the information you have. You ask for the next piece of information. You do that loop until you reach your endpoint. And within that, you have a knowledge base of either parameters, what's the cutoff of a normal, let's say, sleep apnea metric, and also what are the criteria for making a diagnosis of Alzheimer's dementia. So you combine these within a workflow manager to make these decisions. Within the institutional level now, you have your protocol where you acquire your data, or you have electronic questionnaires where you can acquire data in more efficient ways to minimize cost and time. And these are fed into the edge services. There you have your local edge data lake, where you can use it also for your clinical purposes, which can have personal health information. But then that is where data are depersonalized and then fed into the cloud services for further analysis. So coming to the metadata manager, I like this tool a lot. You heard from all projects about ontological representation. What I like here is that we developed something that allows representing abstract categories of variables across dimensions. First of all, where the source of a certain variable comes from, then whether it represents an amplitude effect, so how big of an effect you observe, or how long you have had it. I mean, at a meeting. Sorry, guys. And then whether it represents elements of memory, let's say a mini-mental test, a cognitive test, or whether it represents a cortisol level, which has to do with a certain inflammatory pathway. So it's not just this is the variable and a single ontology, but actually a multi-dimensional ontological representation. And that's useful because when your workflow manager says that, hey, I'm missing this variable that has to do with sleep, and it is acquired through neurophysiology with a sleep study, it's easy to create flows, simple flows, that are very abstract, but know to look at what is the source of acquiring it. So when you want to create these flows, you don't have to do an individual flow for everything. I know I'm getting into details, but for people interested in that, it's very powerful. And of course, you can have your questionnaires translated easily to different languages and so on. Analytics. So beyond just being a data repository, you do want to do stuff with all your data. And that allows for not just a simple, let's say, t-test or classification test, but let's say you want to do a volumetric test on your brain. So you have tools here that are open source that you can actually say your right hippocampus has this volume. This is one or more standard deviations, let's say, below the mean. So that is a component that you can feed into your decision flows. Or you have an EEG viewer, which also includes a polysomnography viewer, where you can review studies that have to do with sleep. So it's not just simple statistics. We're talking about more complex data analysis. And I want to highlight some features of going beyond just anonymization, but actually depersonalization in our approach. So following not just GDPR, but being very rigorous, if you want, ourselves. When you are uploading an MRI image, beyond just taking out the name of person, we know that you can reconstruct the person's face through different techniques. So what we do here is you actually deconstruct whatever you have into something that is nonsensical or a distorted facial feature, so that you can upload such an image, respecting privacy. And coming now to the thing that, if you want, binds the different components, and that's the expert system. So in order to do things, you want to follow a flow. So you can create such flows, and you can use them or create them at the abstraction level as you desire. You can make a flow that's very abstract that calls on other flows, or you can make it very specific to a specific, let's say, compare means, which would be a simple 2-3 step flow. Take the data set, filter it, and then just compare the means between these two data. So all of these components together. I want to close with some ethical considerations as we move forward to more, if you want, unsupervised AI tools. Our tools are, if you want, in the majority, almost all, are following supervised approaches. They do follow respect for human rights, privacy, and values. And importantly, we do have, first of all, as a consortium, we do follow principles of including vulnerable population, underserved populations, with the ability to see the flows and what data exists there. There's full transparency, so you know that if you're saying that if somebody has such variable below a certain value is abnormal, you know that this was derived based on potentially even all white older men, for example, or it was indeed derived out of a set of people that are coming from diverse backgrounds. And in the end, it is the clinician or the researcher who is responsible for the decisions made. Following in medical ethics, the 4 basic principles of beneficence, non-maleficence, justice, and autonomy. Just to close with this slide on the interpretability and explainability of AI, as we have formed our approach with our workflows, with our metadata manager, and knowledge of the different tools that we have integrated, we know or we're able to interpret why a model, in this case, makes a particular prediction. Now, it could be that you create a fully interpretable model. What does that mean? It would be a model where you have a simple regression or a classification function. You know exactly that that's the coefficient within this variable. Or also you can implement model agnostic interpretability techniques where these help understand why a model leads to prediction without necessarily knowing the inner workings of certain models, but by identifying weights on a certain feature significance after using permutation and so forth. So this is an overview of where we are. We're reaching our last year at this point, and we're already validating the different components. We'll very soon have research output out by using the platform, and within the next 4 or 5 months, we'll have a clinical expert system implementation, validation testing within the clinic. Thank you.
Okay, thanks to LSS, the last of our presenters today. So I would like to move the webinar on to the discussion section. And I'd invite all the presenters today to open their cameras so we can all discuss together. So I think I will start things off with a question which came from the chat, which is for the resample team, specifically for something which Christos was talking about the open data. This question came from Tatiana, and she asks, what is the % of people who agreed for their data to be anonymized in any given time point in the project request regarding open data. Christos, are you able to take this question?
Thank you also, Tatiana, for the question. I don't have the exact percentage of the patients involved in the studies. Maybe Anki can help, but it's the hospitals actually know this information. But so far, we haven't heard any patient that disagreed on this policy, on applying this policy, participating in the study. We have, I think we're now ending up formulating the new open data access forms for the resample project, which will be applied at the end of the project. So far, we don't have any patients disagreed on participating. If I'm wrong, Anki can correct me.
Yeah, that's totally right, Christos. So we, in the information letter to the patients, we describe the purposes of processing. And as we have two parts in the example, the first part is what we just presented on the real-world data collection. And in that part, if a participant agrees to participate in resample, he or she also agrees with that the anonymized data can be shared to further research on all the elements that we described in the letter. And for the second part, so the virtual companionship program, we will ask new informed consents also regarding the open research data. So that will be included. But I have not heard anybody or no patient that did not want to participate because of anonymization of data. So that was not a point that the potential participants did hesitate about so far.
Okay, and then Tatiana is in the chat again saying, do people opt in or out of sharing that data?
Opt in.
Opt in. And then before I move on to the next question on this point of open data, perhaps retention and MES-CoBraD could share if they're approaching this point in a similar way or if that's being considered within their projects, the open data.
Yeah. So the data is planned to be open following FAIR principles. The idea is that you have data, or you want to analyze data, because it's not just having them, you want to analyze it, right? So providing all the tools to analyze it within the platform. So that's the main approach at this point that is the most straightforward. There are a couple of considerations I want to clarify, because it is a big thing across projects, the anonymization. So by default, we anonymize all data that go to the cloud. That's not a question, unless you just keep it into the Edge module. There are some additional components of control, and that has to do, first of all, with personal health information variables. So as you define a variable in the metadata manager, you have your own workspace, or you have a collaborative workspace as well. So if you as sales, let's say, you have your workspace, or as an institution, NIA have a workspace, but then you work in MES-CoBraD, you also have the MES-CoBraD workspace. This allows you to share variables you have already created within that collaborative workspace. Then you have people that say, hey, I don't want these data to be shared with other institutions, or I want my data to be shared with us institution. Or something that exists quite a bit, especially in the United States, is I don't want my data, even if anonymized, to be shared with for-profit organizations. So in that case, having that approach where you can actually tag which participants allow this access more broadly, allows you to upload the data within the platform, and then depending on how the user has entered. So if you're a researcher at an academic institution, you have access to all of the anonymized data. But if you are a for-profit company, you may have a subset on that. Again, there are actually laws that, to my understanding, and we don't have our, I don't think Sergi is here from our legal partner. But as long as data are fully anonymized to the greater benefit of society, they can be shared outwards. I mean, there are some IRB components that are followed in that process. Yeah, I don't know if I answered all of the questions in that sense. Sorry.
Yeah, no, thank you. I think you also touched on the question from Tatiana in the chat as well. So I will move on to a question that I have for retention, specifically for Mary. In the presentation, you discussed the retention semantic model. Why do you feel the semantic model approach is the most appropriate for processing retention's heterogeneous data?
Okay, thank you, Oliver, for your question. So we think that semantic data model is, let's say, the most appropriate approach for processing heterogeneous data due to its ability to provide the structure and meaningful representation of data, enable better integration, understanding, and analysis. For example, the advantage of the semantic data model includes explicit semantics that capture the meaning and the relationships between data elements, and allows for more precise and, let's say, unambiguous representation of data, which is crucial when you deal with diverse data sources. Also, another advantage of the semantic data model is that establishes a common vocabulary, ensuring that different data sources share a consistent understanding of terms and concepts, and this facilitates the communication across the different systems. There are a lot of other advantages. I can say one more. For example, the interoperability. The semantic data model promotes interoperability to provide a shared semantic framework. So the systems that adhere to the same semantic model can easily exchange and understand the information, regardless of differences in data structures or formats.
Okay, thank you.
Thank you.
Yeah, if any of the other projects have thoughts or reflections to jump in when you're hearing one of the other projects speak, feel free to take the floor. Otherwise, I can move on to a question for resample again. Again for Christos. So you mentioned federated learning briefly in the presentation, but I wondered how the use of federated learning makes matters more complicated when it comes to data protection.
Actually, this is a tough question. It was one of the things that we're struggling with still, and we're learning also, to be honest, as a privacy engineer on that. The challenging part is, well, if you have an algorithm programmed by a person, okay, so you know the data involved, and you know the output. And you know, for a given set of data, the given output that you will get. And so you can handle things more easily and accordingly, let's say. Okay, with AI involved, and especially with federated learning, where you have different data types involved and try to get the results for different hospitals, you want to do the functionality in 100%, okay, but you need to understand which traces you leave when you use AI algorithms. Even if some answers, like, for example, do the models per se are a threat, or only when they are accompanied by data? This is something that we always have in mind, and we try to examine when we use AI algorithms, where you leave traces, and based on the new threats and the new landscape of threats and attacks, how far back you can come to for example, to the data that's used for training. Maybe for AI researchers and specialists, these things are more easy to handle with, but for a privacy engineer that tries to identify privacy gaps and privacy issues, and it's quite challenging for us, because this thing is evolving very fast, and in parallel, we try to keep it trustworthy and safe throughout the process. So we open various boxes where we start new discussions on that. But this is how research progresses, actually, for our field as well. And I think this was one of the more demanding parts from our perspective when we're dealing with the compliance issues, but also from the actual technical satisfaction of privacy requirements. So actually, to give it a shorter answer, with federated learning, we inherit all the AI capabilities, but also the AI known and unknown areas where privacy pops up. So we try to handle this accordingly.
Okay, great. And I'm sure by opening these boxes, this is where the innovation comes from.
Exactly.
You need to bring
Yes.
these people into conversation, and this is where the real innovation in these projects.
Yeah. That's why it was for me and for our group, we're very thrilled to deal with this project, because it's not only the output, as I said in the presentation, it's also the internal things that you need to cover and do it properly in order to reach out the outcome safely and in a trustworthy manner. So it's also the internal parts that we're dealing with during the development. So it's not like we have the solution and we try to apply it, but we do research for our own consortium for putting things straight at the beginning.
Yeah, I can see some of the other presenters nodding, so it sounds like an experience which is shared. I will jump back to Eliseos and MES-CoBraD with another question. Towards the end of your presentation, you showed us the metadata manager. And I wondered how the abstract categories in the metadata manager can help research or clinical practice.
So I briefly touched on the example in clinical settings. So for example, you have a flow from your expert system that says, okay, get the next information you need for a chief complaint. So get, let's say, the AHI, the apnea-hypopnea index, to predict whether somebody has sleep apnea. So the flow goes to the metadata manager and sees, okay, what's the source of the AHI? It's actually polysomnography. So you can instantly feed it back to the expert system and say, ask the patient to do a polysomnogram. So that's a simple thing. So from a programmer's perspective, a coder's perspective of creating such a flow, it's very simple, because you can use a single flow that applies to all the types of metadata in such an approach, rather than saying, if you have AHI, do this, if you have the other one, do that. So that's the clinical expertise. Now, let's say you're a researcher and you want to compare how sleep duration affects outcomes of cognition. So you have a linear flow where you say, I want to see how total sleep time affects things. Now, total sleep time, you can measure it from questionnaires, you can measure it from actigraphy, you can measure it from sleep studies. So as a concept, it's a single concept, but the sources of real-world data that you can have it from are multiple. These sources on a conceptual level go into the abstract categories in what we have now as health-related, if you want, categories. And within that tree of abstract categories, you would go into sleep and then sleep duration. And you would represent, instead of going into the individual variable, you would pursue the abstract category, allowing you to instantly combine different types of total sleep time. Now, of course, total sleep time accuracy with actigraphy is different, or what it represents is different compared to self-reported total sleep time. But it gives you that ability when you're talking about combining bigger data and also thinking on a conceptual level. And you can do z-scores in that as a scientist. You can harmonize in different ways to say that's the mean, that's this patient is 1 standard deviation above the mean, or whatever. So you can do the analysis that way.
Okay, thank you. I'm aware of the time, so I'll move on to some more general questions, and the projects can jump in as you see fit. So, as you reflect on the work of your projects, what are some of the key lessons learned in working with real-world data, and what future directions do you envisage for the application of real-world data in medical research and healthcare?
Okay. Yes.
Go.
Okay.
Eliseos, you were
No.
Just going to.
I wasn't sure where it was.
I'm going to repeat a little bit the challenge with other words now, because the future directions. Well, I believe from our perspective, I mean, from the data protection perspective, we talked about the challenges before. I think that the challenges run through all type of projects like that. It's not only the samples. We don't claim that we're unique on that issues. But dealing with real-world data is actually something challenging, especially when you are dealing with systems that go across different, let's say, countries, different legislations, let's say. So different rules. Now we're on a safe side because we're under the EU. So all the partners are having a common framework for dealing with real-world data. But imagine that if this goes in a more global solution, then I am sure that on top of the all technical issues that we mentioned so far, aligning with different legislations is something that is very common. I think we all have that in mind when we're dealing with type of systems. And because the fact is that, well, actually, I'm talking as my role as a member of the Hellenic Data Protection Authority, we've seen a lot of misalignments with EU regulations and data protection facts from companies that are not in EU-based, but offer solutions in EU. And we see a lot of things that we believe now that we're dealing on our research bubble where things are go fast and more progressive. We see, you know, we're dealing with details where in fact, in actual cases, more basic problems are not solved yet in the industry. Things that we consider as solved and we're dealing with details, we see that the major issues, especially for data protection, for example, how we do the anonymization is not clear for many partners that they don't have the scientific personnel to do so. They believe, for example, that pseudo-anonymization is the same as anonymization. We see that a lot. So I think for me, the problem is not finding research, actual research and good research on these topics, but it's how this research and these outcomes will end up on the basis of the developers to enhance that in their activities when they're designing this type of system that they use real-world data, especially in the medical sector, but not only in the medical sector. So I think that one of the issues that I understand is the other way around.
And do the other projects have something they want to share on this, or a key lesson learned from working with real-world data as we draw to the end of the webinar?
I just wanted to add it very shortly that we also need to keep in mind, at least from a resample perspective, the patient's view and preferences and needs that they want to be included here. And that's really also a challenge because real data that we are collecting is also changing during the time. So yeah, that's also a thing that I just wanted to add it to Christos' thing.
Also, I would like to agree with Professor Kalionatis about the privacy and also the anonymization of the data. This is a big issue. We will see also in the future more details about this, how we save the scenery. So I would also like to mention that we have to continue the efforts in order to integrate the real-world evidence into the regulatory decision-making processes. And this involves the collaboration with regulatory agencies in order to establish standards and also methodologies for using real-world data to support the post-market surveillance.
And Eliseos, for MES-CoBraD, do you want a final word on this point?
Yeah, well, a couple of things. The one is I'm thinking more and more about how do we aim with all the real world data, not all data really in medical practice, for a European health data space, which means that if I collect data here and I go to Italy, that my data, if I see an expert there, they can access it following principles. I mean, in the United States, a lot of these things have been addressed with Care Everywhere or similar approaches, but you do need elements such as a unique identification number or something that can identify you within the European Union or globally, potentially. And there, the issue will be that if such a thing exists, that you aim for a European health data space, it also means that a lot of your data will be still able to be in silos that are protected. So yes, you can transfer it in an anonymized way from one silo to another, or make it accessible. But the need for that unique identifier existing also means that somebody can potentially also know where you will be. So there won't be a solution, a realistic solution, the way I can think of it, that things will always be at some level pseudo-anonymized if you want a clinical practice. Because true anonymization would be you wouldn't be able to revert back in the end to the source. But that's okay, as long as you put all the other necessary blocks in the way, or limiting the chances that such an exposure of personal information would be out there. And that means from the simple thing of just sharing the minimum necessary information to also taking away, stripping it from information that is within that data set that is unnecessary, like defacing in addition to anonymizing and so forth. That's from that component. Other components are that you have a lot of new technologies that come out. For example, in our case, Philips stopped producing their ActiveWatch, which is the only one that has been approved for research purposes for actigraphy. So now all the Fitbit and other wearable devices will take the lead in that, but each one will have their own data formats. So you need also, like you have for DICOM images for imaging, like EDF for polysomnography and epilepsy data, you would need something similar for categories of data acquired through new technologies. And that doesn't yet exist in such a way to allow easy harmonization and interoperability.
Okay, thank you. I feel like we're just broaching topics which the discussion could really, points that we could really continue talking on, but we're 5 minutes over time. So I'll wrap things up at this point. I would just like to say a big thank you to all of the participants who joined us today and the speakers who spent time preparing their presentations. It's great to see the projects side by side and talk about these similar challenges. And I'm sure there'll be another opportunity for us to do this again. The presentations will be made available and the recording will be made available. And I'm sure if you have specific questions for the speakers to continue the discussion, you can get in touch with them personally as well. So thank you, everyone. I'll let you get on with the rest of your day. Yes, I'll close the session now. Thanks again.
Thank you.
Thank you,
Thank
Oliver.
you.
Thank you.
Bye.
Bye-bye.